So this is the reason for which we are looking for values for sin I and sin R. But the consideration for this is that we look at normal incidence. And what we mean by normal incidence is that we are considering very small angles. Now again for okay. Very small angles of incidence. Very small angle of incidence I. Now, automatically, because R depends on I, when you pick very small angles of I, R will also be small. And at normal incidence, sin I is equal to tan I. And sin R is also equal to tan R. So instead of even considering sin I and sin R, let's even go straight to look out for tan I and tan R because they are equal. Please, are we okay? So when we consider this triangle ACD, tan I is equal to the opposite, which is CD over the adjacent, which is AC. And tan R, which is triangle BCD, would be equal to CD over BC. Please, are we okay? Are we fine? Then we substitute it into our ratio. The refractive index from water to air is equal to, this is equal to tan I over tan R. So you go ahead and substitute the values of tan I and tan R you obtain. So we have CD over AC. Okay, all divided by times the reciprocal. Times BC over CD. This would give you BC over AC. BC over AC. But you see, what is this? This is the refractive index of light from water to air. But we will want to express this in absolute terms. And that will be from air to water. And since we know that the refractive index, okay, from the absolute refractive index would always be, this is from air to water, is equal to 1 over the refractive index from water to air. So this would certainly be 1 over this value, BC over AC, which will be equal to AC over BC. Okay, then when we do this, it means we have expressed the refractive index of this in absolute terms. Please, are we okay? Hello, are we okay?
Yes, please.
Yes, please.
Okay. Hence, the absolute refractive index of this is equal to, we have AC over BC. Now, what is AC? AC from our diagram is the real depth. Over BC. BC is the apparent depth. Okay, so for vertical displacement of light, the absolute refractive index of a material is expressed in terms of its depth, real depth over apparent depth. So whenever an object is placed, okay, in a material and it is being viewed, the refractive index of the material, the denser material, can be obtained by considering its real depth over the apparent depth. And so, well, the concept does not demand that you prove this, but you have to understand why in a situation like this, the refractive index is expressed as real depth over apparent depth. The syllabus actually does not demand that you prove, but you have to understand. Please, is that okay? Now, the next thing you have to understand is that, yes, this is the real depth, which we are representing as R. Or, yes, just R. And then this is the apparent depth. It is measured from the surface of the water or of the denser medium. So this distance is the apparent depth A. Okay. Now, from here, from the original position of the object to its virtual position is the extent to which it's been displaced vertically. So we call this as the vertical displacement or normal displacement. Normal because it's like perpendicular displacement. So when we look at this, we realize that the real depth R is equal to the apparent depth plus the vertical or normal displacement D. And so whenever you are asked to calculate for D, then D is equal to R minus A, meaning D is equal to real depth minus the apparent depth. That's what I mean. We can also remodify something, and that is, what is R? R is AC. So AC minus, what is A? A is BC. Okay. When I factorize out AC, I have 1 minus BC over AC. In fact, when you multiply it through, you get the same thing as what I have here. Are we okay with this? Are we okay?
Yes.
Oh.
But Mr. Edia,
hello.
Mr. Edia, please, this is from like the very beginning. Please, you see that the object itself cannot produce light. Does it mean that the light that is incident from it is actually reflected light?
The thing is that, Akofala, we see as a result of reflection of light or refraction of light. If I can, you can see me because light from the bulb around incident on me and reflect to the camera for your eye to pick. Is that okay? So in the same way, if you are looking at an object in water or in place within a denser medium, then the light around which incident on it would have to reflect or come from the object, and because it is moving from a denser to a less dense medium, be refracted before it gets to the observer. Okay, so it means so long as there's a source of light around, light would move from the object and then be refracted through the denser medium when it gets to the less dense before an observer can see. Are you answered?
Yes, please. Thank you.
Go.
Mr. Edia,
Hello.
please, if we weren't considering small angles, then we wouldn't have to use tan, right?
Yes. Yes.
Okay, thank you.
But you see, for this theory, optics, light theory, the focal length, 1 over f, we come up with those theory by considering small angles. Is that okay? We come up with those theory by considering small angles and so on and so forth. Don't forget paraxial rays.
Please.
Small. So that's the condition for attainment of those theories. Okay. Now, supposing the real depth is D. So here we are considering, okay, before that, AC over 1 minus. Now, we are saying that the absolute refractive index is AC over BC. Okay. Are we fine? So look at this. This is BC. If absolute refractive index is AC over BC, then we have BC over AC. Then it means that if you make it as BC over AC, you have 1 over the refractive index of the material. So it means that this thing here is equal to 1 over the absolute refractive index. Are we okay? Absolute refractive index is equal to AC over BC. So if you have BC over AC, then it means it's the reciprocal of this. And so we are substituting this as 1 over N. Okay, so if the real depth is H, then the displacement is equal to 1 minus 1 over the absolute refractive index of the material. And this is another way, formula or expression to determine D. In fact, D can be obtained from here, no doubt about that. But this is another way we can express the same vertical displacement. So all that you have to understand is that for vertical displacement, the refractive index is equal to the real depth over the apparent depth. The displacement D can be obtained from the real depth minus the apparent depth, or the product of the real depth into bracket 1 minus the inverse of the refractive index. This is the concept, okay, for your understanding. Any question? Please, any question? If you have any question, quickly bring it up. If you don't have any question, we move on. Adubi, are you okay?
Yeah.
All right. The next thing you have to understand is this. Refraction in triangular. Please, if you are writing, hurry up. Let me see if I can give you a question on this. If we can solve a question on this.
Please, you can clean it now.
Okay, I'm coming. I want to see if we can get a question under this to solve. Okay, I'll do that. I'll look for the question and then send it to you later on so we can look at it. Okay. So the next thing to look at, Dromo, are you there?
Yes, please.
Hey, today people are quiet. Oh. Refraction of light in triangular prism. And this concept is applied in practical so much. This one, and then refraction in rectangular prism, where we have lateral displacement. We'll be using these two so much in practical. So please take notes. Okay, take notes. Now, what's a triangular prism? The triangular prism, as the name suggests, is a prism shaped like a triangle, the glass block. Those of you who have been coming over to the lab, that rectangular, triangular glass block you see around. Okay, I don't know if you've seen I don't know if you've seen one before. The triangular prism. Those of you who have been coming to the lab. So A, B, C are the parts of the triangle, of the triangular prism. The triangular prism has what we call the refracting angle. Refracting angle or angle of the prism. Angle of the prism.
Hysteria.
Hello.
Please, can you come again with the definition of triangular prism?
Oh, I'm not defining. No, I said, is that a triangular glass block you see in the lab? Okay. So
okay. Thank you.
The angle of the prism or the refracting angle is what we are representing as the letter A. So A is the angle, refracting angle, or the angle of the prism. Each triangular prism has this. Okay. So let me just bring the A at the vertex A. Now, what is so peculiar about the triangular prism? The triangular prism, okay, always has two refracting planes or surfaces. So by its shape, it has two refracting planes or surfaces. Here, the two refracting surfaces are AB and AC. So this side and this side are the parts that refract or bend the path of light. Hey, our number has reduced though. Where are they? Let me check on you. Adelaide is here. Akofala, Anita, Brittany, Deborah, Dromo, Eliana, Hilda, Irene, Kezia, Mary, Matilda, Nanajua, Nana, Anefua. The rest are going to rest. Anefua and Nana Jimfua. Okay. So it has two refracting surfaces, AB and AC. And these are the parts that deviates the path of light. Okay. Now, the advantage of the triangular prism over the rectangular prism is that the rectangular prism, let me draw something. This is how it is. This is the rectangular prism. This is the normal. Whenever light incidents at this side, yes, it will deviate the path of light. Over here, it will cancel out. So refracting at the first, this side cancels out. That's how come I is equal to R. I is equal to E for parallel plates medium. Refraction in a parallel plate. For triangular prism, the deviation of light over here, this is the normal. When light hits on the first refracting surface is AB, it is bent towards the normal. When it gets here, it is bent away from the normal. The advantage of the rectangular triangular prism over the rectangular prism is that the deviation which occurs here and then the deviation occurring here, AC, is combined to give you a larger value of deviation. Okay, so this has the ability to add the deviation at AB to the deviation at AC to give you a wider value of deviation. Unlike this one, which what happens here cancels out here. Okay, and because it is for this reason or for this special property of triangular prisms, that is why it is used for dispersion of light. Dispersion of light. So because it has the ability to add deviation which occurs at one plane and then another plane to give you a wider value of deviation. Okay, that is why this is used to form for dispersion of light, separating light into various white light into various components. Please, are we okay? Are we okay? So that's the advantage this triangular prism has over rectangular prisms. If you have any question, ask so I can continue. All right. Then, hello.
Please, I don't really understand the wider.
What I'm saying is that this part, okay, will refract and will produce a deviation, angle of deviation. This side would also refract, produce angle of deviation. The triangular prism has the ability to add the deviation which occurs here, deviation which occurs here, to give a wider value of deviation. When we go into details, when we start looking at it into details, you understand what I mean. But deviation of light occurs here, deviation of light occurs here, and it is added up to give a wider deviation. And it is for this reason that the triangular prism is used for dispersion of light, and that is separation of white light into 8 various components. Are you okay?
Yes, please.
Okay. So let me see if we have some. Oh, okay, we have about. So these are the properties. It has 2 refracting surfaces. Now let's incident light at one of the parts AB and see what will happen at the other side, AC. So the normal is always an imaginary line which is perpendicular to the surface. So we are incidenting light at one of the refracting. Hello.
Please, you talk about the dispersion of light there.
Yes. I'm saying that it is the triangular prism that is used for dispersion of light. And dispersion of light is about separation of white light into its various components. Okay. So light is incidented at one of the planes or refracting surfaces. Here is AB. AB. This is the angle of incidence I. When you see light is traveling from less dense medium into a denser medium, and so it will be deviated towards the normal. When it gets to the other refracting surface, AC, it will be deviated again. Let's draw a normal. So this is N1, N2. Okay. Here, the deviation will be away from the normal. Okay. So this is angle of incidence. We call this as angle of emergence. Okay. This we call as the emergent ray. Emergent ray. A ray that is emerging. This is the incident ray. So angle of incidence, incident ray, angle of emergence, emergent ray. Please, are we okay? Hello.
Please, I have a question though.
Ask your question.
Please, you see the incident ray is from air to glass.
Yes.
And the angle of emergence, the image is from glass to air. So why isn't the angle the same as the incident ray since it's the same medium?
I've not said so. I've not said so.
Please, I'm asking why it's tilting downwards.
Oh,
I don't know if you get.
This is the normal. And once the ray is coming from glass to air, it will deviate away from the normal. Okay, it will deviate away from the normal. This is the normal, N2.
Yes, please. Okay.
Are you okay?
Yes, please. Thank you.
It will deviate away from the normal. That's why this is widening. Okay. Now, let me extend the part of the incident ray, the original part. Meaning, ideally, this is where it's supposed to go. Ideally, this must be the path, isn't it? Let's also extend the part of this. Ideally, this must be where it has to go. It may not be straight. So this must be the original part. But because it is traveling from denser medium to less, that's why its part is deviated. But the extended broken lines represent the original part of the incident ray and the emergent ray. Please, are we okay? Are we okay?
Yes, please.
Good. The angle from the normal, this is a refracted ray within the prism. So the angle between the refracted ray and the normal is the angle of refraction, but to the first plane. So R1. The angle between the normal to the refracted ray is the second angle of refraction, R2. So R1 to the first plane, R2 to the second plane, AC. When we extend the normal to join, we have something like this. Now, it means that if this is the original part and the ray is deviated, this must be the deviation, isn't it? This must be the deviation, angle of deviation. Are we okay? So, sigma 1, the angle between the refracted ray and then the original part of the incident ray, this becomes the angle of deviation to the first plane. So, sigma 1, okay? Listen, in refraction, let me revise this with you. Air to glass. Whenever light is moving from air to glass, it will be deviated away towards the normal, isn't it? This is the angle of refraction. When I extend the original part of the incident ray, this is the angle of deviation. This is the angle of incidence. You realize that I is equal to R plus sigma, isn't it? Okay. So when you make sigma the subject, this is equal to I minus R. That's the same thing we are doing here. This I is equal to the whole of this angle. So if this is the angle of refraction R1 to the first refracting surface AB, then the other remaining angle, which is I minus R1, must be equal to the first deviation sigma 1. Please, are we okay? Are we okay?
Please. You stay there.
Hello. Oh, I'm asking you, are you okay with what I said so far?
Yes, please.
When we look at it at the other plane, this part, we have the same thing. The angle of emergence must be equal to this angle plus this angle. Okay, so E is equal to, this E is equal to R2 plus this second deviation, sigma 1. Sigma, 2. So when you make sigma 2 the subject, you have E minus R2. And this is the expression for the second deviation which occurs over here at AC, meaning AB, its deviation is this. AB's deviation is this. AC's deviation is equal to this. I told you that deviation occurs here, deviation occurs here, but triangular prism has the ability to add. So this becomes the total deviation. The total deviation sigma, big sigma. It means that the total deviation is equal to sigma 1 plus sigma 2. Okay, it has the ability to combine the deviation which will occur here and here to form a larger or maximum value of deviation. If you have any question, ask before we continue.
You say there, please. I got lost at sigma.
Where?
I can't really see the board very well though, but the sigma 1.
Okay. All right. So let me. Oh, it's 55. Okay. We have Friday. Friday, we'll look at it again from the scratch on refraction in triangular prism. Okay. So for now, we have just looked at it on the surface. We'll look at it into detail again. Then, because here it's a bit technical, but I have to still break it down to your understanding. And when you understand it, doing the practicals and all that becomes so easier. So we shall look at it once more on Friday. Is that okay?
Yes,
so,
please.
I draw the curtains on today's meeting here. God willing, we'll have another fruitful session on Friday. Good night to all of you and bye-bye.
Bye.